Did any exciting or burning questions come up during the coffee break? Okay, it better be exciting or burning. Just kidding, yeah.
Is it possible to consistently add the axiom of choice?
I think on its own the answer is yes. Yeah. And in fact, I'm pretty sure it's defined in one of the standard libraries somewhere. Hello, 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 yeah. Any other questions? Okay, let's get right back to it. Okay, where were we? So we had just seen how to define inductively, we saw how to define inductive properties of a particular piece of data as an inductive data type, right? And the even example we saw was just defining a property on one particular data type, in this case nats, right? But you can, there's nothing restricting us to just one. Defining a property of a single data type, we can define it over multiple ones. And in particular, we can define a two-argument proposition or a relation as an inductive data type as well, right? So here's an example of how we might define less than or equal to as an inductive data type in Coq. So here LE is less than or equal to, as you might expect. And what's the right way to read this? Well, we're going to build a new kind of proposition that on two different natural numbers. And in particular, we're going to say there are two ways of building up evidence of this proposition, and correspondingly two constructors, right? So we're going to say every natural number is less than or equal to itself, which is true. And also, it is the case that if one natural number is less than or equal to some other, it's also the case that it's less than or equal to a successor, or adding one to that number, right? And then we have a nice notation here. And you can imagine using these rules to build up a proof that any particular number is less than another one by first applying less than or equal to n, and then just applying successor as many times as you need to get to the the number in the right-hand side of the inequality. Yeah. All right. So here are some sanity checks. I guess we'll work through these in class. Let's see, just to see get a little bit more experience of using these inductively defined propositions or relation in action. Let's see. I guess I wish there was some way of hiding these proofs. Is this readable to the people in the back, or should I blow it up slightly more? I see thumbs up. Okay. Right. So if we want to show that 3 is less than 3, well, we have the constructor for we just need to apply that constructor, len, and we're done. If we want to show 3 is less than 6, we can do what I said before. We'll just reduce this to showing that 3 is less than 5. And then 3 is less than 4, and then 3 is less than 3, and then we can apply the constructor len. I guess we could have also applied this proof that we just wrote up above for convenience, and we're done. Interestingly, again, if we have some evidence, inconsistent evidence as an assumption, we can do inversion on it to derive a contradiction. So here we're saying, if you give me some evidence that 2 is less than 1, I can give you a proof that 2 plus 2 is equal to 5, right? And when we do inversion on H1, there are two cases to consider. In one case, it would have to be the case that 2 are equal to 1. So LE1 is just not even considered. That's obviously not true. And inversion discharges that case automatically. And then alternatively, there's the case that 2 was less than or equal to 0, and from which the LENS thing, so we add 1 to 0, and we get the original conclusion, right? So once we've done that, let's see, where's H2 here? So we have this proof that 2 is less than or equal to 0. If we do inversion on that, we're done. Because there is no number such that adding 1 to it will get us to 0, and 2 is not equal to 0. So the two cases are just discharged automatically by inversion. So sort of the key bit here is that if we have some piece of evidence, if we have some assumption about an inductively defined proposition or relation that's inconsistent, that's obviously contradictory, it is possible to derive those contradictions, derive false from it, using the inversion tactic. Yep. Any questions about that? Yeah.
Inversion is about the injectivity of constructors and their disjointness. But here, we don't have any equality of constructors proposing injectivity or disjointness claims. So what is inversion doing?
The question is, what is inversion doing here? With the assertion that inversion is about proving injectivity and disjointness of constructors. And the answer to that question is inversion is actually a hammer that is doing many things in addition to just reasoning with those facts. And and we're going to see precisely exactly, we're going to get into a little bit more detail about how inversion works later in this lecture. So we'll revisit that question when we get to that point, okay? But the sort of key takeaway is that inversion is doing more than just proving these constructors are disjoint. In particular, you can imagine it's showing there is no way that you could have applied a rule to derive this particular proposition that you have as an assumption, because it's inconsistent with the ways we have of building up that evidence.
Since inversion is such a big hammer, is there a simpler way or a simpler tactic to use to discharge this proof?
The question was, could we use a simpler tactic to discharge this proof? The answer is yes, but it would be more tedious too. So in some sense, if you have a contradiction, it's best to bring out the largest hammer you have. Which is, I guess, a little bit wishy-washy of an answer. But yeah, we could discharge this in other ways. It would get, yeah, I'll leave it there. Okay. Any other questions? Okay. Okay, we worked those sanity checks. So now that we've defined this we have this inductively defined relation, less than or equal to, we can also define strictly less than, right, as in terms of this inductive data type. So as an example, we can say that a number n is less than m if it's the case that adding 1 to that number is less than or equal to m. So we don't actually need to define an additional inductively defined proposition or relation in order to define less than or equal to, or strictly less than. Here are a couple more examples of relations on numbers, right? Here's square of next nat, next even. I think what's sort of an interesting and cool thing to note here is that if we defined square of, if we define this as like a Boolean function, how would we do this? Well, what we'd probably have to do is figure out some way of, well, I don't know. One way to do it would be define like a factorization function and see if you can factor this into a square of two numbers, and then see if these two factors are the same and they're equal to the one that you passed in. So you have to do this computationally. This inductively defined proposition, you don't have to worry about any of that, right? It's very declarative. There's no sort of information about how to algorithmically compute this square, right? It's all sort of embedded into this declaration. So in this way, inductively defined propositions can often be much nicer to write and use to specify properties than their Boolean counterparts. Yeah. Are there any questions about that? Yeah.
So the first two types you've written can be rendered in terms of the equality proposition, but instead you've decided to make them as inductives. Would we want to use equality with functions in place of these kind of inductives? Or what kind of power do these give us instead of using equality and functions?
Right. So I think certainly in the first two cases, there's nothing really. These don't really add anything on top of equality, in much the same way that this LT, the strictly less than, doesn't really add anything on less than or equal to. It's just sort of a nice convenience. So practically speaking, I don't think working with defining square of or next nat as equality, as definitions in a similar way to LT, would be any nicer than working with these inductive data type definitions. I don't think you'd buy anything. Where it does come into use, really nice use, is if you have multiple cases, like here, this is much nicer to work with than having big disjoint, like sequences of ORs, right? So if you think about defining fix, that function, the in function that we defined before that like iterated over a list and built up a bunch of disjunctions, it's a little bit more natural to have two different rules for that, right? You'd have a rule for it's the head, and you'd have a rule for when it's a member of the tail. And so in that case, when you have multiple, basically multiple cases, inductive is much nicer to work with. In addition, it doesn't have to be total. And in addition, if we defined in inductively, we don't have to worry about putting this sort of spurious false case, right? We just, oh wait, forget I said that. We're going to see that in a second. Okay. Are there any other questions? Okay, right. So to see a more in-depth example of inductively defined propositions that aren't even or less than, we have this little case study in Software Foundations of how we could embed a really simple language, which using and define properties on it using these inductively defined data types. And you can imagine as the week progresses, you're going to use the concepts for this simple language to generalize to actual programming languages and properties of those programming languages and programs written in those programming languages. So this is sort of like the simplest example of a little, we'll call it a programming language that you might want to reason about. And it has a lot of the features that these larger examples will also have. Okay, so here's our regular expression data type. What are our constructors? I don't think there's anything exciting here. There's an empty set, there's the empty string, there's characters, there's sequencing or app is what it's called. There's union and there's star. I think this is a pretty reasonable subset of the regular expression language if it's not total. Of course, by itself, there's nothing, so this is just an inductive data type. We could build up trees using these constructors, but there's no meaning associated with them, right? So how are we going to assign some meaning to terms, some semantics to terms built up using these constructors? And here's what we're going to do. We're actually going to come up with a set of rules that relate a regular expression to a particular string. And these will give some sort of semantics for how we can interpret a particular regular expression. Okay? So how are we going to think about this? Let's think about what the matching rules for regular expressions are. Okay. I guess they're all written on the slide. I probably should have waited and had you. So like for instance, empty set doesn't match anything, right? The empty string matches the empty string. Okay, that makes sense. The char matches the one character string with exactly the character in it. App matches the append of two strings and so on and so forth. Perhaps most interestingly, right, when does union match something? Well, there are two cases there, right? Either the string matches the first regular expression or it matches the second regular expression, right? And then, well, otherwise straightforward. As a special case, the sequence of strings may be empty. So star re always matches the empty string no matter what the regular expression is, right? Okay, so here are the rules for matching regular expressions in English. I hope people think they seem sensible. How can we embed those as an inductive data type? Well, basically we're going to have one rule for each of those English clauses, the English sentences we had up there. So here we go. We're going to define a new proposition. It's going to be a relation on lists of, we'll say characters, in this case T. It's an arbitrary type. And then there's going to be a regular expression, and then there'll be a proposition. And this is going to embody all of the possible ways that a particular string of characters could be matched by a regular expression. So there's the rule for empty, namely if it's the empty string, we're good. If it's a concrete character, then it's only going to match the char constructor. Mmap looks straightforward. Interestingly, for the union constructor, we're going to have two different rules, right? One saying we match the first regular expression, one saying we match the second regular expression, right? And then For star, we're going to have a special rule distinguishing when we match the empty string. We always match the empty string. And for app, it's what you'd expect. So hopefully these look relatively straightforward. There's basically a one-to-one correspondence with the rules on the English rules. There's also a one-to-one correspondence with these in the definition of this matching construct as an inductive relation. So here are the rules for it. We're going to have the special tilde equal tilde syntax for matching. But this should look fairly recognizable to anyone who's familiar with inference rules, right? And again, there's one rule per constructor of this inductively defined relation. Any questions about this? You could imagine doing something simpler for a programming language, right, where you have, instead of a regular expression, you have a program, and then you assign some meaning to it as an additional part of the relation. Okay, so here's a good question, and this answer is a question we had earlier, I think asking about if we needed a rule for even one. So in this, we had this clause in our English definition, right, that said the expression empty set does not match any string. We don't actually have that corresponding rule in our set of definition, in the definition of our inductive relation. Do we need to add something to account for this English definition? So think about it. Don't answer yet. I will, and then I'll ask you to raise your hand. Or raise your hands when you have the answer. Okay. What's the answer? 1, 2, or 3? 3. Right. No, the lack of a rule actually gives us the behavior we want. Okay. And why is this? Someone want to volunteer to? Yeah, go ahead.
Because of the
Okay.
don't remember
Because it's not derivable.
Right. So if we ever, that's exactly right. If we ever had as an assumption that the empty set matched some string, we could use inversion on it, and it would, that would be a contradiction. There is no way of building up evidence of this fact. It's just not allowed. And so in some sense, in much the same way that these rules allow us precisely specify exactly which values are included in the relation, which means they also precisely specify which values are not included in the relation by exclusion, right? So excluding something from this relation is just a matter of making sure there are no rules that can be applied to derive it. Right? We don't need to explicitly call it out. Yes?
Would it be useful to add a lemma saying that no string would match the empty set?
Yep. So I think the question was, would it be useful to add a lemma, witnessing the fact that that empty string doesn't match any string? And indeed, I think that would be very useful, right? You can derive this fact from the definition of the inductive data type, and that's a very useful sort of sanity check that will probably be of use when you're working with assumptions of this form. Yeah, that's a great suggestion. And indeed, these sorts of sublemmas, sort of verifying that your specification actually meets your informal mental specification or your English specification, can be quite useful. Yep. Do I want to say anything else about that? I think I don't want to say anything else about that. Because it might get confusing. Okay, so let's just see a couple of examples of this relation in action, right? So we can actually essentially test the sanity of our relation by seeing if the values we want to be included into it actually are included, right? And how do we do that? Well, we can just build up proofs that show particular strings and regular expressions are included in the relation. So as an example, we can show that the list with 1 in it matches the regular expression char1. We just apply the constructor. That's pretty straightforward. Similarly for app, we can do the same thing by just applying these constructors. And then finally, here's an example. We want to show that something is not included in the relation. So how do we do that? We're going to want to derive false. So we say it is not the case, using logical not, that that the list containing 1 and 2 matches the regular expression char1. And how do we prove that? So we say, again, just to drive the point home, this is equivalent to saying this statement implies false. We're going to intros the assumption, this assumption about whether or not the string matches the regular expression, and then we'll do inversion on it, and it'll just completely discharge the goal. Okay. Is that, okay, that's great. So, right. So, let's see. Right. So what is interesting here? So here's an idea. This is just an example of how you might validate another way of validating that your rules are correct. Here we're just going to define a function that takes a list of characters and copies it verbatim into the precise pattern that would match it, right? And then we can show once and for all that this property holds, although we're going to do it on a concrete list here. So we're going to say, what does this function expand out to? It's just going to be app char1, app char2, app char3, app empty string, or empty string on the end. So we can show that this is going to work, that these values are included in the relation by just applying the constructors over and over again. I don't think there's anything too interesting there to go into. Here's a much more interesting example of something you might want to validate about your about this relation. Okay, so what does this say in English? This says for any string and some regular expression, if that string matches that regular expression, if the regular expression matches the string, well, either way, it must be the case that that string also matches any number of repetitions of that regular expression, right? Okay. And so why is this an interesting property to prove? Again, recall that when we wrote down these rules, we could have gotten it wrong. There could have been a typo, right? We might have forgotten to include a root we actually wanted. So at some level, it makes sense to step back and actually write a couple lemmas about that actually verify that the things you expect to be in this inductively defined data type are what you expect, right? The things you expect to be in there are actually in there, and that these rules conform with your internal sort of your internal notion of what this property is, what properties this relation is supposed to be establishing, right? And this is a reasonable sanity check, because again, Coq doesn't check anything about these inductively defined propositions, right? It's relying on you to give it good information or a good specification. It just makes sure that they're syntactically well formed. Yep, okay. I won't say anything more about that. So let's see an example of that in action. Let's see m star 1. So how is this going to work? Well, intros, as we would expect. App nil r. I guess we proved this lemma before, that we can always append nil to the end of the list. That's what we're going to do here. And now we can directly apply the m star app rule, which, if you recall, says that a string appended to another one will match a regular expression, a star of a regular expression, if the first string matches the regular expression and the second string matches the other regular expression. Okay, so why did we have to do this rewriting step here? Why couldn't we just apply this rule directly? What would happen? I'll process it, but. Right. So let's see we'll see what happens. Okay, so we get an error. Why do we get an error? Oops. So if you look at the conclusion of that m star app rule, it is very specific. It is expecting the string to be of the form one string appended to another one, right? And if the string is not of that form, this rule does not apply. They are not syntactically the same. And Coq, in this case, is not smart enough to figure out on its own that appending nil to the end of the string is the same as produces the same value as the original string. So we have to do a little bit of massaging in order to apply this rule so that everything matches up as Coq expects. So here, if we just, let me step out. We have to do this rewrite. We apply this, and we are good. So now we have this as an assumption. We're done. And here we can use that extra special rule we added, saying that the empty string matches regular expression star, always matches regular expression star, and we're done. Okay. So I'm going to do this. Oh yeah, I'm going to try and do something a little bit on the fly here and see what happens. So suppose we had done this instead. Suppose we say that we're just going to peel something off the end. Is this safe? I don't know. But no, I'm not going to do this. Never mind. I get into trouble. I guess I didn't try. Okay, so I apologize. I encourage you in your free time to try and switch those rules and see how the proof has to be adapted in order to make it go through. Okay. So, right. Naturally, if we have, because as we saw with even, when you have these inductively defined relations of propositions and you're reasoning about them, typically you're going to need some information about the subtree, the subtree that's used in the proof, right? So induction is often demanded for these inductively defined propositions, and X match is no different. Okay, so right, so here's one for you. If a regular expression matches some string S, then all elements of S must occur as character literals somewhere in RE. And this is precisely because we don't have any sort of wildcard operator in this regular expression language, right? So how are we going to set up this proof? So this intuitively makes sense, but in order to formulate this in Coq, we're going to have to go through a couple of extra steps, right? We're going to have to formalize what it means for all elements of S. What are the elements of S, right? We're going to have have some way of extracting those out. And then we're going to need to have some way of expressing what it means for a character to occur in a particular regular expression, right? So let's look at what fixed point RE chars is going to do. Well, it's just going to recurse over the structure of the regular expression. Every time it hits a char, it's going to add that to the list of literals. And then it's going to append things appropriately as it works on the subtrees. Yeah. In the case of what it means for a particular character to be inside a string, we're going to rely on the definition of in that we had from our previous chapter, whose name I can't remember right now. So we're going to use that. And because we're using that in, we're going to also rely on this fact that we had, that we proved in that chapter. I guess from logic. Here's the proof. It just says that if a element appears in two lists appended to each other, it must be the case that it either appears in the first part of the list, or it appeared in the second part of the list. And this intuitively makes sense, right? So now that we've done that, we can formulate precisely this informal definition we had before in Coq. So here it says, if we have some string that matches a regular expression, and if there is some particular character that appears in that string, then it must be the case that that character also appears in the list that we got from running this character extraction function over the regular expression, right? And let's see how that works in action. There we go. So intros. Here we're going to do induction over the how this regular expression was built up. Okay, and we're going to get several cases here. One for each of our rules in this match proposition. I think most of these are relatively straightforward. The interesting case, of course, is, well, there are really two interesting cases. One where we use the char matching rule. in which case we're going to need to evaluate this RE-chars function that extracts the characters out. So this is going to give us either x prime equals x or false, but from our definition of n up a simple n, this is precisely what we have up above, so we can apply it directly, and we're done. Another interesting case is where you need the sum lemma about when an element is included in two lists appended to each other. So right up here, right, we have as an assumption that either x was included in the first part of the string or the second part of the string that matched against this app regular expression. Okay, so now we can, oh right, so we're going to rewrite. I skipped over this part of logic, but it is possible to use the rewrite tactic to apply if and only if rules. So what's actually going on here is, if you recall that our in-app if lemma had the form if and only if. And so when we rewrite with it, if we have a goal or an assumption that precisely matches the left or the right-hand side of that if and only if, we can replace it with the other one, if that makes sense. So here we're going to replace this in x, two strings appended to each other, with the or. And it also is going to work down here in the conclusion. And if you want to see how that works, I encourage you to read in logic. There's a little section about set-ord rewriting that gives you more details on all the exact machinery. Okay, but once we have that in hand, we now know that either x had to be in the first part of the list, or had to be in the first string, or it's in the second string, right? And now we can just use our destruct tactic because we have an or, and that's going to give us two cases, one for the first one for the second one. And now we can just apply our inductive hypotheses using left to prove the left-hand branch of the conclusion and right for the other one. And then these other rules very much follow immediately, or these other cases very much follow immediately in a similar case. Oh, except this one, which is worth discussing, I guess. Right. So this is actually yeah, right. So what's interesting here is that now we get two induction hypotheses, which correspond to the two subparts of the M-star rule. So if you recall, the M-star rule said, A, the string had to match the regular expression. The first part of the string had to match the regular expression, and then the tail of the string had to match the star of the regular expression, right? So there are essentially two. The proof tree has two branches that continue to can continue to apply the rules for this inductive proposition to build up this evidence, right? And correspondingly, we get two inductive hypotheses, one corresponding to the branch on the left-hand side of the proof tree and one corresponding to the branch on the right-hand side of the proof tree. And we can use those. Here, this corresponds to the left-hand side, this corresponds to the right-hand side, and we can use those when we're proving this thing, basically. So there are two cases. One, it was either in the first part of the string or the second part of the string, and we'll use one of these induction hypotheses for either cases. So if it was in the first part of the string, we'll use the induction hypothesis for the left-hand branch of the proof tree. If it was in the second part of the string, we'll use the right-hand branch. And we're done. Okay. I need a drink. Are there any questions so far? Okay. That's worrisome. Okay. So the remember tactic. Okay. So there's one unpleasant thing about working with induction that and similar destruct that you may have come up across when you were working on your exercises, or may not have yet. But induction has, if you try and induct over a piece of evidence that isn't sufficiently general in the sense that it's talking about something that's too specific, it can lose information. And the best way to see this is to actually see what it looks like in action here. So here, what does this say? So this says that if S1 matches regular expression star and S2 matches regular expression star, and then appending those strings together will also match regular expression star, right? So if we try and do induction over the first hypothesis, there's an issue here, and that is, whereas before we had this assumption that this string matched some arbitrary regular expression, here we're a little bit more specific, right? This says this is matching a particular regular expression, star something more general, right? And this is going to be problematic when we try and do induction. So it's best to just see what comes out. In the m-empty case, there's nothing particularly interesting. It works out as expected. The other cases are a little bit more problematic. So we're going to move to that next case. So what happens here? So here, we have to show that the second string matched some character x prime, and that x prime appended to S2 is matches char of x prime here. But this is problematic because we've lost this, this bit of information about the star, right? The star that we had wrapping this original RE has completely disappeared. And in fact, if you look at the rules, there's no way to construct this bit of evidence, right? So if we pull in, or construct this conclusion. So if we do an intros and we do inversion on H, now we're stuck showing that x prime appended to x prime matches char of x prime. And this is clearly not false. There's clearly no way of building up this goal. Okay, so what happened here? Where did things go terribly, terribly wrong? So the issue is that when you do induction over a particular judgment, it only works if the values that are used in that judgment are completely general. So if they have the form, some constructor of that data type applied to some other things, that gets lost completely. That information just disappears along the way. And that's precisely what happened here. So, and the reasons for this have to go into how induction is set up and how it works under the hood. But we're not going to get into that. We're just going to see one way to work around it. So one way to work around it is to just force the thing we're inducting over to be completely general. And we can do that by just adding this equality, right? So we'll just say, oh, there's some new regular expression RE prime, and it's equal to star RE. And S1 is going to match this new regular expression. And now when we do induction over this, we actually have this equality in scope, and we can use that equality to do some rewriting, and the proof will go through. But as the slide notes, this works, but it's sort of ugly, and we're sort of complicating the statement of our lemma to account for some of the deficiencies in how the induction tactic works. So it turns out there's a better way to do it, which is the remember tactic, which is what we led with here. So the remember tactic is a useful tool to have in your arsenal when you're doing proofs by induction over these inductively defined relations. So what does remember do? Remember E as x does the following things. First, it replaces all occurrences of the expression E that you're remembering with some new variable x, and it adds an equation, x equals E, to the context. So in other words, if we're in this star app case here, and we say remember star RE as RE prime, we're going to get into the same proof state that we would have for that original uglier lemma definition that we had on the previous slide, this particular formulation of star app. Right? And now, once this stuff is in scope, we have this extra bit of information in all of the inductive cases, which is going to allow it to work. So let's go to that proof right here. So here's star app again. We're going to do remember, and now we get this extra equality, and we get this new RE prime related to this the original RE. We're going to call generalized dependent to stuff some stuff back in the goal, so we have a sufficiently general inductive hypothesis. And now we're going to do induction over this more completely general match proposition, where there's no extra information encoded in the values that we're making a judgment on. So now when we do induction, okay, this case is not so interesting. But now, note that here in the mchar case, which is precisely where we got stuck, we have this extra assumption that character of x is equal to star of regular expression, which is a contradiction. And we can just discharge all of these things. So in fact, all of the cases where we would have gotten stuck before are now completely discharged because they're not syntactically equal to our original regular expression. So now, in the case we get to where we actually have a star, well, now this is no longer contradictory, but because we have this equality as an assumption, we can use the injectivity of the constructor to get the fact that the star regular expression, this R double E prime, is in fact our original regular expression. So we're going to do inversion on it. And now, the good bit is, when we're matching the second string, we now know something about the regular expression we're matching against, namely it's a star, or star pattern, and it just falls right out. And a similar thing happens in the other case. I don't know why this is getting highlighted here. And we're done. So I guess the take-home message here is if ever you're doing a proof of induction in Coq and you find yourself with not enough like you're getting into these cases that are obviously somehow contradictory, it might be worth going back and looking at the thing you did induction over and see if you're losing some bit of information when you're doing induction. And if you are, pull the remember tactic out of your bag of tricks and apply it, and it will to generalize the thing you're inducting over, and this will help. Again, this is one of those things, this is one of those sort of practical concerns that you only really recognize after you've been using Coq for a little while. But I think the rule of thumb is if you're ever trying to do induction over, if you ever try and do induction over an inductively defined proposition or relation that has some concrete bit of information in it, you should probably step back and try and use the remember tactic, because that's sort of a bad smell. Rule of thumb. Okay. Okay, right. So, 1 second. I think what I'd like to do is skip. No, I'm going to cover the reflection chapter. This reflection bit's sort of important. Okay, so right. So we saw previously, I guess a couple of hours ago, that it's often helpful to relate a Boolean function or computation to some statement in prop for one of these decision procedures, right? We saw this with even b and this and the even inductive relation that we defined, and also this other formulation is a proposition of what it means to be even, right? Now, it turns out that if we want to now, once we've defined this decision procedure, right, we can judge whether or not a number is even or not by just evaluating the function, right? Or in this case, we can decide whether or not n is equal to m by saying, is the value of Beck-Nat true or false, right? So we can actually evaluate that, and we can say true. We can destruct, as we do here, Beck-Nat n equals nm, and that's going to give us two subcases, one for the case where this function is true, and one for the case where this function is false, or the result of this. Evaluating this function evaluates the false. But this is such a common paradigm where you have a proposition that is decided by some Boolean function that it's useful to not have to jump through as many hoops, because this gets a little bit painful where you actually have to destruct over the Boolean function, and then you do some rewriting with this thing exhibiting that it's equivalent to the proposition. It's such a common sort of reusable paradigm that it makes sense to come up with some more general methodology so you don't have to go through all these hoops every time, because it's annoying apparently. So here's how the trick for doing this. This is a trick you can use for anything. So let's look at it. So here's the idea. We're going to define an inductive proposition that's going to give us a better case analysis principle for a particular decision procedure. Okay, so instead of destructing or generating an equation that Beck-Nat equals true, and then we have to rewrite with this extra lemma, we're just going to use this induction, the principle, reasoning principle that this inductive data type gives us to get the proposition directly. So we'll do a destruct, and we'll immediately get n equals m, or n is even, or whatever the particular property that we want. So let's look at what this inductive data type definition looks like. Okay, so this says we're going to have some arbitrary proposition, and we're going to have it's going to be a relation on an arbitrary proposition, P, a Boolean, right? And yeah, that's it. And there are going to be two ways to construct this evidence of this data type. One is if the proposition is true, then this Boolean also has to be true. And if this proposition is false, well, yeah, this proposition is not true, then this Boolean is false. So what does this tell us? So this tells us if we have an assumption of the form reflect prop P true, we can conclude by inversion on that P. Similarly, if the bool is false, we can conclude not P. And to see why this is interesting, it's probably useful to just look at how it works in practice. So this says, well, actually just what I said before. B is true if and only if P holds. Implies that B reflects P. That is, B is a decision. We can think of it as being a decision procedure for this proposition. Okay. So what's interesting here? So here we go. We want to construct an element of this inductively defined proposition. So we'll just destruct B. Okay. And the case that B was true, right? There's only one way of building up reflect P true. It is the first constructor. And what does that need? We need to give it a proof of P. That's what this subgoal says. But we have as an assumption that B was true if and only if P holds, right? And of course, it's easy to show that P of true equals true. So we know P. And practically speaking, we're going to use this setoid rewrite tactic again, using on if and only if. What does this do? We're going to rewrite with H, and that's going to replace the left-hand side of this if and only if with the right-hand side and wherever we're rewriting. So we're going to get a goal of true equals true. And then we can just use reflexivity to discharge it. In the second case, we need to show it is not the case that P is, well, we need to show not P. So we're going to imply the constructor for the case where B was false. And now we need to show not P. Okay, but this is pretty easy to do because we have down here, I'm going to unfold that. We're going to need to, we need to show that P implies false. Okay, so let's intros P here. And now we can use the rewrite rule to replace this P right here with false equals true. Okay, so we can rewrite H in P. And we have now an assumption that false equals true, which is obviously a contradiction. So if we do inversion on P, we're done. Pretty cool. So we've shown that if we have some proof, if we can show that this Boolean reflects a particular proposition, we can construct evidence that that proposition is true using this reflect tactic. And the advantage of using this over the normal if and only if connective is that if we destruct a hypothesis or a lemma of the form reflect PB, we now have two cases. We have the case where B was true, and we get as an extra bit of information that P also holds as an assumption. And in the other case, we have B was false, in which case not P. So we get immediately, when we do case analysis on this, we either get P or we get not P, and we don't have to do any rewriting with this if statement. So it's helpful to see how this works in practice with a concrete example. So here's what we can do. We can show that BQ_nat accurately reflects this proposition that n equals m. That is a correct decision procedure for it. So we're going to do intros. We apply if and only if reflect, which is what we showed before. And now we just need to show that the soundness of this decision procedure, which we proved previously, so we can rewrite with that, and we're done. Ooh, did that work? There's a lot of tricky things. Okay, so now we jumped through a bunch of hoops here. Let's see why it was actually useful. Okay, so now, in the case before, where we destructed on BQ_nat nm, right? We were destructing on this if statement right here. Now we can destruct this reflected piece of evidence about of BQ_nat reflecting n of m. And what's going to happen? Well, first of all, it's going to replace all occurrences of BQ_nat here. There are going to be two cases, one where this is true, one where this is false. So we're going to replace all occurrences of this with true or false in those two subcases. And we also get an extra bit of information. Namely, we get P in the case that BQ_nat was true, in which case the proof proceeds normally. Or we get a assumption that this proposition did not hold, so not P, or P n not equal to m, in which case the proof proceeds normally. So there were a couple of extra hoops we jumped through here. But the nice thing was, this is like this pattern of destructing a decision procedure and then rewriting with the thing, the proof that's showing this decision procedure sound, and then using that information in the proof is so common that this is actually a very nice way of sort of streamlining that process. So this is a little bit of proof engineering hackery that you might enjoy. So the higher order bit here is that, I said this before, for this simple example where we're just doing these equality tests, the reflection doesn't really seem to add that much, right? But using this reflect predicate often leads to much more shorter and clearer proof scripts, a larger proofs get, because all of the sort of smarts about how that proof proceeded is baked into this decision procedure that we built up. And it's also sort of embedded in reflect to cut out some extra examples. So this property was actually inspired by SS reflect, which you may have heard of. It's this Coq library that's all built around this idea of using decision procedures and reflections for automating proofs and making them more tractable. And this library was used to prove the four-color theorem and the Feit-Thompson theorem quite successfully. And you can read a little bit more about SS reflect here. Yeah. So what is the takeaway bit about this discussion, this digression on reflection? It's that oftentimes, if you're working with propositions that have decidable, that you can write a function that says yes or no, this is true or false. It's often convenient to do so, and then use that function when you're doing your proof developments. Okay. Are there any questions about reflection? Again, it's one of these things that I can tell you that it's useful. But once you start doing your own proofs and you start working with it, you'll see that this is actually a very powerful technique. And you'll have to take my word for it. And you'll only learn by doing, I'm afraid. Maybe I'm not afraid. Okay. If there aren't any questions, I'm going to move into some optional material here that should be pretty interesting. Okay. Okay, this is a cool bit here. So what I want to do for the next half an hour before lunch is dive a little bit more into this relationship between theorem proving and programming, which you may have heard of before. It's occasionally called the Curry-Howard correspondence. And the key insight here is that programming and proving in Coq are the same thing, basically. Proving manipulates evidence or propositions and builds propositions and destructs propositions in the same way that when we write a program, we destruct data and we build data, right? So there was a question earlier about what's the difference between inductively defined propositions and inductively defined data types, and I said, there's no real difference, right? So, and that's right. If like the way we build up evidence or using these rules is in fact some form of data, right? These proof data trees very much can be thought of as data. What are propositions themselves? Well, they're just types, right? So the rules we use to build up a proof tree are the data, and the things they build up are propositions. And what characterizes data? Well, it's type, the type that it builds up. Okay, let's dive into this a little bit more deeply. Okay, so let's look at this definition of even that we gave before again. Okay, right? Hopefully it still looks vaguely familiar. So suppose we took a slightly different way of looking at this definition, right? So when we see this colon, you could think of this as even has the type, nat arrow prop, right? Or you could read it as is a proof of that some natural number satisfies the proposition we're defining. So the constructor ev0, which has type ev0, you could read as ev0 is a proof that 0 is even, right? And it turns out this pun, the fact that you can interpret a type of a particular definition also as a proof of some proposition, or its evidence for that proposition, is called the Curry-Howard correspondence. And it's this observation that there's this deep connection between proving a fact and programming, or writing an algorithm. And that proofs types are roughly equivalent, can be understood as being equivalent to a particular proposition or statement. And a proof can just be thought of some data value exhibiting a witness of that proposition. Yeah?
Was the paper?
What?
Was the paper you refer to?
What is the paper? So this is...
What's the title of the paper?
What is the title? I think it's Propositions as Types, yeah. So the Curry-Howard isomorphism as an idea has been around since the 60s. Like this is an old idea that is constantly rediscovered and reappreciated, and hopefully people in this room will appreciate it a little bit more after this lecture and after the summer school. But Phil Wadler has a really nice, this paper he has is a very nice essay sort of studying the history of this correspondence and some practical applications. So it's definitely worth reading. It's good. I would, and hopefully other people in this room, if they've read it, can attest to that. Yeah. So, okay. And, right, many useful insights follow from this connection. So, right. I think I've been implicitly doing this as I walk through the definitions of this inductive data type, right? Where you can understand this constructor, you could understand it as a function, right? You could say EVSS is a function that you give me a natural number, and you give me some piece of data, EVN, and I will give you a new piece of data that that 2 plus n is EV, right? Another way to read it is that this is a function that you give me a natural number, and you give me a proof that that natural number is even, and I will give you a proof that 2 plus that natural number is also even, right? And I will give, this constructor builds the piece of evidence exhibiting that fact, which concretely realized is as a proof tree. So look at this example right here. So if we, after you write a theorem in Coq, you state the theorem and you walk through the proof script applying some tactics, when it's done, you can use the print command to actually see the underlying proof object that was built up by calling these tactics, okay? So if we say print, it will actually exhibit for you the piece of data or evidence that it built up exhibiting the proposition that you stated in the initial statement of the theorem. And oftentimes this is quite gross, but here it's pretty simple. So if we look at this, what is the proof object we built up under the hood? What does the evidence look like? Well, it is probably what you expect. It just applies the constructor for SS to the application of the constructor, the SS constructor, to the even zero constructor, right? This is very much just a piece of data. It's a sequence of applications of the constructors of this data, which we can interpret as a proof, but we could also interpret as data. I mean, there is no difference here. And indeed, if we wanted to, we don't have to use tactics at all to build the proof of this theorem, right? We could actually manually, we can check the type of this expression that we got out. Interestingly, well, maybe not interestingly, this expression that we built up has precisely the type, the statement of the original theorem, right? There's no distinction. And well, on top of this, we can actually directly build proof objects inside the script itself, right? So instead of calling tactics, we can say apply, and we manually provided this definition that we built up by hand. And because this is a witness, or a proof of the exact goal we're trying to prove, EV4, you can see up here, it just solves the goal immediately. So we're instead of interactively building up this proof script using tactics, we're just telling Coq exactly what to do. Like, here is the concrete proof object.
So
yeah?
This is possible only for inductively defined propositions, or like a proof object?
Nope. You can actually, so I think we're going to get into this, but you can manually construct an expression corresponding to the proof term for any provable proposition in Coq. And because this is precisely what happens under the hood when you're using tactics. Okay. And in fact, it's sort of cool to, when you're walking through the proof of a particular proposition, you can actually ask Coq to show you what the intermediate sort of proof term you're building up looks like using this command show proof. And in fact, I encourage you to do that for some of the simple examples. So let me switch over to this proof objects buffer. It's really instructive to see this in action. So, okay. Okay, so does it? Okay.
Raise it up a little.
Yeah. Okay, so when we start out, what is the proof object we've built up? We don't, hopefully this is readable. We have this question mark goal. So this says there is some hole, we need to fill it in completely. We haven't constructed any underlying object, okay? So we haven't done anything. But after we apply this tactic, or after we apply this proof rule, what do we have now? Well, now we see under the hood what we've built up is a partial proof object, right? It's the application of this constructor to some subterm, some sub-goal, right? And intuitively, the type of this hole, right, is exactly the proposition we're trying to prove up right up there, right? So think about it. If I want to prove that 4 is even, what do I need to prove? I need to prove that 2 is even. So I need a proof object exhibiting that fact. That is the type that is our goal up here. And it's also the type of this hole, of this explicit proof term we're building up. So as we walk through this proof, we apply the next one. And of course, we have application of this constructor twice. And then we can apply the constructor that, for showing that 0 is even. And if we show the proof, well, now that there are no more sub-goals, this means there are no more holes in the underlying term that we need to fill in, right? So we've completely finished the proof. And in fact, when you hit QED, what happened, all Coq is doing is it takes this proof term that you've built up with no more holes in it, it does a quick final type checking step, and then it assigns that definition to this identifier that you defined the theorem with, that you were using for the theorem. Yeah?
Sometimes with these proofs, there's more than one way to get to prove it.
Yep.
And so if I did a different proof to get the conclusion, and I said, show me that, print that proof object, would I see the?
It would be different. It would be different. Yeah. So if you can imagine, if we had EVSS prime, which had the exact same, the constructor had the exact same assumptions as EVSS, it just had a different thing. If we applied that, then in the underlying proof term, when we applied that constructor, that is the constructor you would see in the proof term.
So this is,
right?
Like the idea where you say intuitionistic sort of thinking.
Yes.
A proposition is identified with the set of its proofs. And so all of these proof objects we build up are sort of inhabitants of the type of the proposition, which is the theorem that we've proven.
That is exactly,
that in turn belongs to the prop.
That is exactly right. Cool. That is exactly right. So the question was, well, the question was, in this Curry-Howard isomorphism interpretation, all the possible proofs or proof objects of a particular proposition precisely correspond to the different ways we can construct evidence of that proof. So everything that has a certain type corresponds to a proof of that type. And that is precisely the intuition or the correspondence we're exploiting in Coq here. Okay, so it's worth noting that these tactic proofs are a way of interactively building up these rather complex terms and expressions, right? When we're calling tactics, we're doing rewriting. The underlying proof terms can actually get a little ugly to the point where it might be cumbersome to build them up by hand. So it's making it more convenient to build up these objects, but it's not necessary. You could, as I said before, just write down everything manually, explicitly write out the proof term. As long as it has the type of the proposition that you're trying to prove, you're golden. Right? So for this rather simple EV underscore proving that 4 is even, we can just use definition instead of theorem and just give it the proof term directly. And this is fine. This is morally speaking, this is the exact same thing as our first interactive proof, our second interactive proof, where we used apply, our third interactive proof, where I can't remember what we did, and then this final one where we just used a definition. These are all the same proof term under the hood. The only difference is how we constructed them, using tactics or giving the manual evidence. Yeah?
What would be the proof object for an axiom or an admitted proof?
So you're saying, what would the proof object be for an axiom? The answer to that is that an axiom has no admitted proof object. If you can imagine, it asserts it effectively asserts there is some proof object with this type, but it doesn't say what that is. So that constant sort of represents the proof object, but it's not. It's abstract. It's just an identifier with of that type. Yeah.
In your current proof state, you can form a term of type T. How can you just assign that to a new variable?
If you
like definition. Like, I know how to do it at the top level, but how can you do that?
Oh. So you're asking, can you define new constants inside a proof script? This is actually a bad proof taste in the sense that you probably should not do it inside a proof script because, in fact, I'm not even. Let me see. I don't think you can. And here's the issue. So when you're working inside a proof script, right, you could imagine writing a definition that might depend on some variables in the context, right, some assumptions that you have. And outside of that particular proof script, that definition, those terms aren't in scope. So if you could define a definition that way, it might allow some terms to escape because those might be open if you refer to that definition outside the proof you're working on. So generally speaking, if you want to define a new object or expression, you should do it outside of the proof script. Every sort of proof script should be self-contained. And there are a couple of notable exceptions, but I don't know if that is a satisfying answer, but yeah. Yep.
So the Curry-Howard correspondence is giving us this correspondence between propositions and types.
Yeah.
Yet Coq is explicitly distinguishing between the two by having type and prop.
Right.
Give us a kind of information why that's a good idea.
Right, right. So the question was, okay, if props and types are the same thing, and that's what I keep saying over and over, why do we bother distinguishing between a prop and a type at all, right? If they're equivalent, why do we make this distinction in Coq? And the answer to that question is has to do with an idea that's come up a couple of times in reference to extraction. So we actually build up these Galena programs, and we might actually want to extract them to OCaml or equivalent functional programs. And morally speaking, the idea is that when we say something has type prop, we're saying these have no computational relevance, and when you do extraction, you can just throw these terms away, right? Because they're not useful when you're actually computing the functions. So morally speaking, it's you could think of it as only being there as an identifier that these are just to be interpreted as proofs and can be discarded freely. I think.
So the types are extracted, and the props are not.
Yes, or set. That's exactly right. Yeah.
So if I write a proof of a theorem, and if you write a proof of the same theorem, will our proof objects match?
It depends. So the question is, if I write a proof of a theorem and you write a proof of a theorem, will our proof objects match? The answer is, it depends. Like if we built it in the same way, right?
So effectively reconstructing two terms of the same type.
Yes. Well, think about it this way. If I'm struggling to come up with a non-trivial example. Suppose that you asked me to write a plus function, and you wrote a plus function. We might write different functions, right? But they're going to have the same type, right? And I might have an error in my plus function because maybe I'm not that good a coder, I don't know. And then they would have different results too. So there's no guarantee just from the type that the term that inhabits it is the same, right? Or maybe here's a better way to say it. If I define foo, it's a magic constant of type nat, I might say it's 0, and you might define it to be 3, right? I don't know. So we could write down different definitions of foo. They're going to have the same type, but concretely the underlying data that inhabits that type are different. And the same thing can be true for like proofs, right? In fact, there are an infinite number of ways of constructing natural numbers. So it's very unlikely we would have coincided. But sort of the important point here regarding like computational irrelevance is for proofs, we don't care what the proof object is. All we care about is that it exists. And so it's not going to impact, we're not going to do anything with these proofs computationally. We're only going to use them, pass them as assumptions to other proofs. So it doesn't matter how they were constructed, as long as we're choosing to interpret them as propositions. And this is sort of a key difference between, the key moral difference between propositions and types, and why they actually make this distinction between prop and type when you're doing extraction, because you're saying, okay, you don't actually need to compute with these proofs under the hood. Okay, yeah?
So even though Coq has types and has propositions, we cannot encode the correspondence within Coq, because as you just said, for propositions, we only care about whether they exist or do not exist, whereas in general, types may have multiple inhabitants. And so it's a correspondence and not an isomorphism.
The question was, can we encode the Curry-Howard isomorphism in Coq itself? We probably can't because it's a correspondence and not an isomorphism. So there is no direct mapping between types and props. I'm struggling to I'm struggling to interpret this question in a way that I can answer it satisfyingly. Here's what I'll say as an answer. So in Coq, you cannot use a prop, something that lives in prop, to build something of type. But you can use something of type to build something of type prop. So, and the reason for that is that prop is not props are not computationally relevant. So there's no way of doing there's no way of matching on them in such a way that you could construct a different computationally relevant piece of data. And that is all I want to say about that, I think. We could talk more offline if you want.
But it is called the Curry Howard isomorphism.
Yeah, so the isomorphism is, or some people call it a correspondence, right? It's just, this is more of a philosophical isomorphism or correspondence. It's like noticing that this connection exists rather than actually asserting some deep, well, I mean, it is sort of a deep mathematical result, but it's a little bit hard to formalize. It's more of a philosophical argument, I would say. Yeah. It truly is a sort of a worldview of looking at choosing to interpret things in two different ways and noticing they can be interpreted. Two things that seem on the surface to be quite different are in fact very related. Let's see some more examples of that. Do we? Okay, we got 20 minutes. 10 minutes. I think what I'd really like to get to is this sort of interesting idea. So it turns out that there is nothing stopping us from building up functions or definitions using tactics. It turns out in much the same way that you could build up this proof object under the hood using tactics, you can actually build up functions using tactics in Coq. You can actually use these tactics as powerful metaprogramming assistants to help you build up, say, an add function here. So to see what happens, I think it's worth looking under the hood for this add1 definition. And we're going to print the proof all along the way. Okay, so when we start out, again, we have nothing in hand. What we're trying to do here is we're trying to build an inhabitant of the type nat arrow nat. So this is a function, right? So what does intro do? How do we build up terms of type x arrow y? What is the constructor? Anyone?
Have you used intro before? It seems like we've always been using intros.
You can imagine intros is isomorphic. I mean, intro is just saying, I'm only going to introduce one thing. So, in fact, well, yeah. Okay, so after we intro, what do we have under the hood? Well, we said, okay, what intro does is it says, if I want to build something x arrow y, I can build it up using as a function, right, as a lambda term. So under the hood, I've built up a function, right, and I have a goal. The goal corresponds to this goal state. Now, if you think, this might be a little advanced, but if you think about what's going on here, here we're trying to build up a term with the type nat, but it's inside a function body. So what do we get inside a function body? Well, we have access to all of the arguments of that function, right? So everything above the line, our set of assumptions here, correspond to arguments that are bound by some function type, or by some function lambda term. Okay, so now what can we do? So what is the type of S? It has type nat arrow nat. So we can apply S, right? Another way, yeah. And now under the hood, what do we have? Well, we have a new goal. Again, it has type nat, and we have a nat in scope. But the proof object, or the object term we're constructing under the hood, actually has an S that's sort of partially filled in the hole, and now we have a new goal. And then, of course, we can apply our assumption and hit defined, and now we have this add function that does exactly what we thought it would. It's going to add 1 to its argument. Okay, so here's another way of thinking of it. When we see, if we're looking at interpreting, let's say, x arrow y logically, what is one way of thinking of it? It says if x, then y. Under the Curry-Howard isomorphism, if we choose to think of this as a function, it says this x arrow y, or x implies y, means if you give me some evidence that x holds, I will produce for you evidence that y holds, right? Now, what is NAT? NAT is a particularly weak proposition in some sense, right? But what we're saying here is this function definition says, if you give me some NAT, I will give you a new NAT, right? If you give me some inhabitant of this type, or some proof of this proposition, although NAT itself isn't a proposition, I will give you a new inhabitant of that type, right? So implication is just function abstraction, right? It shows you how, given an evidence of something, I can build an evidence of something else. And of course, just as we can compute with this evidence, right? So what happens under the hood if I evaluate add 1 applied to 2, right? It's going to take a concrete inhabitant, the concrete inhabitant 2, and it's actually going to produce a new number 3, right? It'll construct that data type of type NAT. In a similar way, when we partially apply proofs to some other piece of evidence, it's actually building up, in theory, under the hood, it would actually build up a complete proof term where we filled in all occurrences of that assumption with the argument, that the evidence that you supplied to it. But because proofs aren't computationally relevant, it doesn't actually build these terms under the hood. It doesn't have to, because you're never going to do anything interesting with them. It's just sort of manipulating evidence around. So, okay, oh right, this is actually really, really key. So you've noticed, well, you've probably noticed that in all of our proofs, when we write a theorem or a lemma, we always terminate the proof script with QED, right? And this actually has a very specific meaning in Coq. It tells the proof checker, or Coq itself, that the term you're constructed can be treated as opaque. And you never actually have to unfold this definition or do anything with the proof term you built under the hood. So why do we do this? It's because these proof terms can actually be quite complex and gross. And if we actually did try and compute with them, we would build up these massive terms and it would be quite slow. And we never actually want to do that. So QED says, oh, don't worry about that. But if we're actually building up a function like add in here, like we do with add in here, and we want to actually compute with it and evaluate it and actually inspect the term that we built up, you need to use this special defined identifier. And this says, okay, take the term that you've built up and actually make it so I can unfold it and use that definition later on. So if we hit QED here, so here's the key difference. So I used QED instead of defined at the end of this definition command. And now when I compute add 1, 2, note that it didn't actually unfold this definition or compute with it anyway. It just sort of left that opaque. It didn't unfold the definition. Because, again, we don't actually care about what these proof terms actually look like. So the key bit here is if you ever use tactics to define a function, which actually can be quite useful if we're using defining very dependently typed functions, and you'll probably see many examples of that later in the week. Use defined at the end instead of QED, or else you won't be able to do anything interesting with it. You won't actually be able to compute with it. Right. And with that, maybe I'll just answer more questions as necessary about this Curry-Howard isomorphism correspondence. I encourage everyone to, at some point, go and actually look at this optional proof objects chapter and walk through the exercises and the examples. Maybe after you've done some more regular programming exercises. And it can be a very eye-opening experience for what's actually going on under the hood in Coq. And proving in general. Yeah, one last.
More of an Emacs question. Is there a way to make the show proof persistent? Do you know?
I don't off the top of my head know if there's some default way to do that. No, I don't. And I will say that generally speaking, you won't want to do that because these proof objects can get, just for kicks and giggles, let's see what the proof object built up for this looks like, for this filter not empty n.